Okay, welcome everyone. It's a great pleasure to have Zhaoyu Han today as our speaker. Zhaoyu got his PhD degree in physics from Stanford last year, and then he has been working as a postdoc at Harvard. Over the years, Zhaoyu has constructed many interesting models. Some are related to fractional quantum Hall states, some are about quantum spin liquids using only electron folding interactions. And there's also another class of models which are frustration-free, and they are able to generate many interesting symmetry breaking orders or other orders. And I believe this is the topic today. Okay, Zhaoyu, please go ahead.
Okay. Thank you, Liu Jing, for the nice introduction and for inviting me. Yeah, and today I'll be talking about some of our recent constructions of frustration-free Hamiltonians. But before everything, I think it's not too late to say Happy Lunar New Year, and I wish you a frustration-free 2025. Okay, as physicists who study quantum many-body systems, especially the strongly coupled ones, we all know how hard it is to obtain an exact solution to the problems that we're interested. Basically, all the Hamiltonians given by the nature are not solvable. So what do we do? Of course, we should directly face the problems and always try to improve our techniques to attack them. But there's also another attitude that is, since it's hard to obtain exact answers to interesting questions, why don't we first try to construct exact questions to interesting answers? That is, we can sometimes first construct solvable Hamiltonians whose ground states are what we want, and then we try to see what these engineered questions can teach us. But specifically, in what aspects could this seemingly concessive method potentially be useful? Well, I believe there are at least 3 points. First, they can be used to unambiguously prove the existence and illuminate the key properties of exotic phase of matter. Especially at the early stage of the study of the matter, they can be very conveniently providing some intuitive pictures for us to think in mind. For example, the famous AKLT model helped the discovery of edge modes of symmetry-protected topological states, and the Haldane-Trugman-Kivelson pseudopotential model justified the energetic stability of Laughlin states in quantum Hall problems. And I think I don't need to go on and list all these famous examples and their glorious history in quantum matter physics to prove their importance. And second, sometimes by luck, we find that the solvable models constructed are actually hidden in the phase diagram of some realistic Hamiltonians. So my favorite example in this category is the Kitaev honeycomb model. And it's clear that when he wrote down this model, it was purely a mathematical construction. But later people found that the Hamiltonian of certain ruthenium chloride is actually not very far from it. And when this happens, we can often conveniently analyze the problem perturbatively in powers of distance to the solvable limit. And on the other hand, the solvable models can now serve as meaningful benchmarks for numerical studies. And these points can guide people to find this phase of interest and saving huge amount of money and time. And third, since we have entered the modern era of quantum many-body physics and are gaining more and more control of quantum systems on engineered platforms like Rydberg arrays and multi-layer 2D materials, I believe that the importance of defining the exact questions to the interesting answers will be just more and more significant, because we'll have a larger and larger notion of realistic, phase space to search for interesting phases. And we need to have a more active attitude to know what we want and how we can get them. And these are the 3 reasons that attracted me into this subject. And I look forward to hearing what you think can be added to this list. So among all these different quantum problems that are exactly solvable, there is an important class of them, called frustration-free Hamiltonians. So specifically, a frustration-free Hamiltonian is a sum of terms whose spectra are bounded from below. And since the absolute value of energy is not meaningful, we can always shift these terms to be positive semi-definite. And the crucial condition for it to be frustration-free is that all these elementary components can be simultaneously annihilate the same quantum state psi, which means that all the components are minimized by the same state. So this psi must be the exact ground state of the system. Many non-solvable models can be reorganized into such a form. And this condition looks tantalizingly simple. However, it is actually very difficult to construct such a Hamiltonian in a meaningful way. Here, by meaningful, I mean that we don't want some highly non-local Hamiltonian such as, psi cat and psi bra, nor do we want to construct models for some boring local product states that contain no spatial correlation at all. Instead, we want constructions that are as realistic as possible while targeting some non-trivial correlated states. And if you give it a try, you'll find that this is a very difficult task. What makes the situation worse is that even diagnosing whether a given Hamiltonian is frustration-free is an NP and QMA hard problem, meaning that neither classical nor quantum computers can really help us on this. So this leads to the natural question: is there any general strategy to construct such frustration-free models? And the answer is fortunately yes, and today I will describe two such schemes and their applications.
A question.
Yeah.
So NP and QMA hard means it's still decidable?
I think it's in NP complete category. I'm not sure. Yeah, I think it's decidable. Yeah.
Okay.
Yeah.
Mhm.
I mean, of course, if you really have a ground state, you can check whether it minimizes all the terms in a polynomial time.
But
Supposing all.
I think another difficulty is to find a way to decompose the Hamiltonian, right?
Oh yeah, but here I'm even simplifying the problem. Suppose I gave you such a decomposition, you can still not determine whether it's a frustration-free Hamiltonian or not in within polynomial time.
I see. So if I don't give the decomposition, do people know
Yeah.
what is decidable?
I mean, even if the decomposition is given, this is still NP and QM are hard.
I actually
It's
don't
called.
know. I actually don't know about the relation between decidability and whether it's NP hard. I thought undecidable is even harder than NP hard.
That's probably true. Yeah, we can talk about this later. Yeah.
Mhm.
I'm not sure I have the answer right now. Yeah. Okay. Yeah. Any other question? Okay. Let's get to the part one of my talk, which will be based on this paper. So the first general scheme I want to introduce is a generalized Wheaton's conjugation method. It starts with any known frustration-free model. In particular, since each gamma alpha term is positive semi-definite, we can take kind of the square root of it and write it as O dagger O, where each O alpha annihilate a known ground state psi naught. Then we can construct a class of other frustration-free Hamiltonians based on this one through a conjugation process. Specifically, we can act the inverse of an arbitrary operator P and its Hermitian conjugate on the right and left-hand side of this old Hamiltonian. And for each term, we can further insert a positive semi-definite operator M alpha between O alpha and O alpha dagger. And it's crucial to note that M alpha do not need to be the same for different alphas. And by this construction, it's easy to see that the new Hamiltonian is still Hermitian and positive semi-definite, and is still frustration-free. And the last point is because we can construct the new ground state psi to be simply p times psi naught. And you can verify that every term in the new Hamiltonian annihilate this state. So this approach may allow us to construct meaningful frustration-free Hamiltonian by properly choosing P and M alpha. Specifically, P will be responsible for introducing non-trivial correlations that you want into the ground state, whereas the M alpha should be chosen to maintain the locality of the resulting Hamiltonian.
Question?
Yes.
Yeah, how much do we know about the uniqueness and whether there's a gap of this Hamiltonian, the uniqueness of the ground state and whether there's a gap?
We know very little because we basically only have a variational approach to determine that. So we only know, part of the information about the spectrum. But yeah, I will talk about what we do know. Yeah.
I see. Thanks.
May I ask something more basic? So P doesn't have to be local, right?
He doesn't have yeah, right.
But if P is not local, so there's no guarantee that the new Hamiltonian edge is local. Or did you choose M alpha such that the new Hamiltonian edge is local?
Yeah, you need to smartly choose M alpha to design M alpha to ensure that the resulting Hamiltonian is still local. Yeah.
I see.
That's
But such M alpha doesn't necessarily exist, right?
Oh yeah, if you just give me a random P, I don't guarantee, reasonable Hamiltonian exist.
I see. Thanks.
Yeah.
Hi, so that's a question.
Mhm.
What does the PSD in the second last line stand for? So what's an abbreviation for that? Yeah.
So you mean what does PSD means positive semi-definite.
Oh, okay.
Yeah,
So
it means
then,
it's Hermitian and
Right.
the non-negative eigenvalues.
okay, thanks.
All right. Okay, this is the general method, and then let's try to apply this method to bosonic systems. So for bosons, there is a class of very simple known frustration-free models taking this form, where each O is defined by two clusters of sites of the same size, L. We call them C and C prime. Okay, and for each cluster C, we can define a big B sub C as a product of the annihilation operators within this cluster. Then OCC prime is simply the difference between BC and BC prime. This form of definition may look unfamiliar to you, but it's nothing but the generalization of non-interacting free boson models with usual positive hopping element. Specifically, when the size of the cluster involved is just 1, the model can just become the familiar free boson model with a special choice of this chemical potential. And all such simple models have very simple ground state manifolds, which consists of all the coherent states in the uniform mode. This is because that when you act each O on any uniform coherent state defined by this, defined by an arbitrary complex number beta, you simply get beta to the L minus beta to the L, which just strictly vanish. And these plain BC states are the boring product states, which has no spatial correlation at all. But we'll see that applying this conjugation method can induce various interesting correlations and exotic phase of matter. Now let's apply this general method. And in our work, we consider a class of relatively simple P operator, which is defined by any real function of the density profile K. Then we know that the new ground state of the conjugated Hamiltonian will be P times the plane BC state. And now you can interpret the P operator as some second quantized form of a gestural-like vector. And it's then probably not surprising if I tell you that the correlations in the ground state map to the classical lattice gas problem of indistinguishable particles defined on the same spatial lattice, where the Boltzmann weight for each configuration is nothing but e to the minus k. Intuitively, you can see that through the fact that all the boson occupation configurations are already contained in this plane BEC state. And now different configurations are having different probability weighted by this e to the minus k factor. And mathematically, this can be seen through the fact that the normalization factor of the ground state is equal to the partition function of this lattice gas problem I just described. And in this perspective, temperature can be just set to 1, and K can be viewed as a classical energy of the occupation configuration, while log beta square play the role of classical chemical potential, which determine the effective density of boson in the system. You can imagine that now any correlation function in a ground state can be converted to some corresponding correlation functions in the lattice gas problem, which can be evaluated efficiently with numerical methods such as Monte Carlo. And especially all the density correlations are exactly the same across these two systems, the quantum and classical systems. And remember that the states we started from are featured as plane BEC states. So all these correlations are kind of printed onto this canvas state by this operator P.
Can you remind me as an exercise, what is oh, you are going to show M alpha. Thanks.
And in some sense, doing this step and you just choose M to be just P squared is actually good enough choice, since as long as these K functions are local, the resulting Hamiltonian is local as well. But if we want to do better to make the Hamiltonian look more physical, we need to do some further engineering by properly choosing these M operators. And specifically, if I want to keep the boson hopping terms in a neat form, I need to choose these special M operators to be inserted between O and O dagger for each term. So I won't torture you by going through all these definitions, but I want to tell you that this is possible, and you can find this general construction in our paper. So these constructed models are actually quite special in many senses. When considering the system and number sectors that correspond to compressible densities, the ground states always have off-diagonal long-range order in spite of dimension of the system, kind of violating the Mermin-Wagner theorem. And the excitation spectrum on top of it has an anomalously soft density mode that goes at least as fast as k squared at long wavelengths. And this can be obtained from variational state ansatz and the fact that the system has translation and charge conservations. And then by inspecting the effective field theory describing these systems, one can find that it has an emergent ISO2 symmetry enlarged from the charge U1 conservation. And all these features indicate that the system lies on a critical boundary between a stable superfluid phase and another phase separations regime. And adding any perturbation will either stabilize the superfluidity or destroy it. On the other hand, this similarity of this of this constructed model to the free boson model is probably not surprising, since these models are conjugated from it. But what is interesting is that when there are hard constraints, meaning that there are some infinite terms in the classical systems, such that the system becomes incompressible, the system could be gapped and many further interesting phenomena could occur. Now let's see the power of...
Can I ask some questions?
Yes.
First, what is ISO2?
ISO2 is a symmetry group of free boson. It's generated by B dagger knot and B knot. So where B naught is the creation, sorry, the annihilation operator in the uniform mode for the boson.
Uh-huh.
So you can check if you check the symmetry of free boson, you know that the Hamiltonian commute with this thing.
Mhm.
And B naught and B naught dagger and the number operator generate a group called ISO2 group.
Okay. Can you explain again what it means to say that the system lies on the critical boundary of a stable superfluid phase?
Oh, it means that any amount of small perturbation will either stabilize a superfluidity or just totally destroy the state, make it unstable to some other order or phase separation.
So do you know the effective field theory of this state?
Yeah, because of effective field theory contains relevant perturbation. I mean, it's a critical theory, and
Yeah.
there's a relevant perturbation to it.
Suppose I fine-tune the coefficient of the relevant perturbation to be zero. What is the effective field theory?
Um, the quick answer is it depends, but the um, but in general, it will be roughly the same as a field theory for free boson, roughly. Yeah.
So what's the difference? I
The
think
difference that here
Mhm.
you can have non-trivial structural factor. You can have, non-trivial dispersion.
But in terms of the effective field theory, I only care about the most relevant kinetic term. I don't care about full dispersion, right? I can look at the band bottom.
Correct. So here, the only additional thing is that the spectrum can become soft at multiple K points.
Uh-huh.
Suppose I choose the P operator, the classical system to be close to some charge ordering. Then in the quantum problem, I'll see Rotan minimum in the spectrum of the, let's say, density mode.
I see. So is it correct that the effective field theory can be viewed, the Lagrangian can be viewed as a sum of multiple Lagrangians, where each of them is the BC transition critical theory?
I mean, if you only care about long wavelength physics, yes, yeah,
I see. Uh-huh.
yeah.
But I'm a bit confused because for that theory, so BC transition theory, the non-relativistic boson theory with chemical potential being zero, for that theory, I don't think there's off-diagonal non-range order, right? When the chemical potential is right at zero.
That's a good point. So I think if you stick to the definition there is of that long range order, it's just that the corresponding TC is zero, and yeah, the critical velocity is zero. Yeah.
Okay.
Yeah, just think about free boson, right? The ground state manifold consists of all these coherent states, and or you can just generate your ground state in charge n sector through acting this creation operator for n times.
But there's also another ground state, which is simply the vacuum.
Oh yeah, so you need to specify your charge sector, right? All the charge sectors are degenerate now. Yeah,
Okay.
that's a peculiar point.
Yeah, I see. Mhm.
Yeah,
Yeah, it is.
yeah, yeah.
Maybe as
But
a
the
side
point
comment,
here, yeah,
maybe
sure.
as a side comment, this system, I feel treating it as a finite system and then taking the thermodynamic limit seem to be more convenient than treating it as an infinite system from the beginning. If we use the formalism of operator algebra to treat it as an infinite system from the beginning, then the first point here may be harder to understand. Because in that case, we were in that language, using the language of C-star algebra, we were just, I think, naively, we will just say that the ground state is the vacuum state. There's no order at all. But there can be non-trivial dynamical correlation.
Yeah. I agree. Yeah.
Mhm. So here you mean when the system is compressible. When the system is incompressible, you mean just by looking at the Hamiltonian, we do not know whether it's compressible?
We need to know the K, right? Like we need to know the K and the charge sector,
I see.
like how many particles we put in.
Thanks.
Yeah, yeah. Okay. Now, let's move on and let's see the power of this construction. So firstly, it unifies kind of a lot of solvable models, such as this quantum dimer model. And to explicitly see this, we can consider the bound lattice of any lattice. Let's take square lattice as an example. And we can choose this classical energy K to be sum over nv squared over all the vertices V, where each nv is a sum of boson number around the vertex. And you can see that this term punishes any deviation of charge density around each vertex from the average value. So when its coefficient goes to infinity, it enforces the dimer covering constraint requisite for the quantum dimer model. And adjusting the boson density of this model can actually further realize like quantum loop model, etc. And similarly, we can obtain effective representation of other solvable models, such as the quantum vertex model. To achieve this, we can put two boson modes on each edge of the lattice, whose occupation represents the direction of an arrow. For example, if boson occupy this side, it means a arrow pointing up, and this represents an arrow pointing down. And properly choosing K function can then achieve the Hilbert space constraint required for the vertex model. Specifically, first we need this edge, the edge interaction to ensure that there is only one boson on each edge. And then you can choose this modified vertex terms to ensure that there are exactly the same number of arrows pointing towards and away from each vertex. Okay. And using similar strategy, we can also construct certain representation of certain 11-1 string net model. And to do that, we just need to assign more modes on each edge of the lattice to represent the different string types. And then properly design K can enforce the required fusion rule of these strings. And there are many other models with interesting ground states that can be constructed. I will only quickly sketch a few here. First, when you choose on-site repulsion in the classical energy, the punishes multi-occupancy for each site, we can obtain a family of models whose ground state interpolate between a plane BEC and a Guth-Wheeler projected BEC state as one turn up these repulsion springs U. And second, when you have some repulsive pairwise classical interaction, we know that the system can develop density wave order that coexist with the superfluidity. So the ground state will be a supersolid. And moreover, when you choose special hopping structures such that the system has dipole conservation, the resulting state is an insulator with off-diagonal long-range order, so the so-called Bose-Einstein insulator can be stabilized here. And lastly, when you choose your hopping structure such that the following conditions are satisfied on a submanifold of the Brillouin zone, the system features gapless excitation on this submanifold. And when the submanifold is not zero-dimensional, the resulting state can be called a Bose metal with Bose surfaces. And there are simply many other examples that can be constructed from this general approach, including some that do not even some models that do not even conserve boson number. But I think these are enough to impress you with the power of this method. And I'm very curious to see further applications.
Question?
Okay.
We go back.
Yeah.
Sorry, go ahead.
I just want to ask, for these examples, how much do we know whether they are other ground states which are not these ones. Some other unexpected ground states.
Yeah, so you are asking about the uniqueness of this ground state, right? So it depends on the connectivity of your hopping structure. In general, it takes some time to prove, but it's provable. Basically, as long as the hopping structure connects all the possible configurations in certain sector, by Perron-Frobenius theorem, we know that this constructed ground state is in certain sector is unique.
Uh-huh.
Yeah, it depends on the connectivity, the ergodicity of the system. Yeah.
Thanks. I think Tiger has a question.
Yeah, I have a more basic question. Can we go to the previous slide?
Sure.
Yeah,
Here?
just to understand the one before. Sorry.
Mm-hmm.
So just looking at these are these Ks the Hamiltonians, right?
Yeah.
But so why are these not just usual frustration-free models? What are the Ps? And I mean, why do we need P to introduce long-range correlation?
So this K is a classical energy. It's not the Hamiltonian.
Uh-huh.
So remember that the way I do the construction is that I use this P operator
I see.
to do the construction, sorry, to do the conjugation from the free boson model.
I see.
Yeah. So any non-trivial correlation is printed by this P operator, which
I
is
see.
defined. Okay. Yeah. So basically, any constraint violating terms are eliminated by this P.
Okay, I see what you mean. Okay, thanks.
Yeah. Yeah. Okay. Any other question?
Can I ask a question about the M operator?
Yes.
So the M operator is defined by the N in the cluster K. Is this always well defined? Like it didn't depend on like the N configuration on other side. So when you define M is truly local?
M itself is not local, but the resulting interaction is local. So you see that my design was to make sure that the resulting Hamiltonian is some kinetic term plus some interaction term.
So you want the interaction term to be local.
Yes.
Okay.
As long as your
I see.
K is.
Okay.
Yeah.
Okay, let me think. Yeah, thank you.
Yeah, hi, I also got a question.
Yeah.
Is there a strategy that tells us how to design a frustration-free model for example, specific physical systems? Because you keep mentioning that we are making the choice, we are designing the system, but is there a strategy to do so?
That's a hard question. I think there's no general strategy. It depends on what you think you define as physical. It depends on what you really want.
So, for example, I have a physical system in experiment, and I'm able to know some of the properties of the model. For example, I know maybe some kind of physical quantities, observables, and I want to design a model that describes a certain phase of this system. And is there a strategy that tells us how to smartly choose the K and M?
Yeah, so it's relatively easier to answer the second part of the question, which is how to choose K.
Okay.
Because now it's basically you want some correlation in your ground state, right? And then you just need to choose the classical problem that does that. Right. For example, if you want some density wave in your ground state, you just choose
Okay.
positive interaction, right? And if you want to enforce some constraint, you just choose the K to punish those configurations that violate the constraint. Yeah, that's a I think, the only general strategy. But the first part is much harder, like how to smartly engineer M such that your resulting Hamiltonian is physical. That depends on a lot of things. That
I
depends
see.
on how you define as physical. So I mean, even our definition is probably not physical for some experimental setup, right? I'm just here just giving you an example to show that this is possible.
I see. Thank you.
Yeah. Okay, so that's first part. It's first general method. If there's no more question, let's march to the part 2. It's a completely different topic. So the second method I want to introduce is called the common commuting order method. And what lies at the center of this method is a fermion bilinear order parameter, O, targeting which we want to construct solvable interacting fermionic Hamiltonians. And for this purpose, suppose we find a set of now let's suppose we can find a set of Hermitian bilinear operators Si at R that all commute with this order parameter. And here I is an abstract index in labeling all different choices of S operator, and R labels its position. And I want to mention that here, I only consider the construction where these S operators are Hermitian, but actually this condition can be kind of loosened to generate another class of solvable models, which is under investigation by me, Jonah, and Islam. But for concreteness, we'll focus on this Hermitian case in this talk. So now let's suppose we find such a set of Hermitian operators. And then I claim that any Hamiltonian constructed in this form has solvable ground states with non-zero expectation value on this order parameter. Specifically, this Hamiltonian can have any positive semi-definite kernel V, which kind of contract different Si and Sg across different places so that the Hamiltonian is overall positive semi-definite. The bracket of this bracket represents the expectation value of S on the ground states that we are going to solve. So in this sense, their value are going to be self-consistently determined. And my claim is that this Hamiltonian is exactly solvable. So let's solve the ground state. To solve this ground state, we define a pseudo Hamiltonian epsilon in this way, which is spiritually similar to a trial mean field Hamiltonian, but it's very different. And it's simply O plus O dagger with an arbitrary relative phase theta. Then, since the pseudo Hamiltonian commutes with the S operators, then any unique eigenstate of epsilon is also an eigenstate of all these S operators. Remember that our construction of Hamiltonian always end with S minus X expectation. This will vanish exactly when acted on any eigenstate of S operator. So suppose we find such a state psi, this psi will have strictly zero energy for the Hamiltonian. And since this Hamiltonian is positive semi-definite, this state is a ground state. Then the task boils down to finding some unique eigenstate of this pseudo-Hamiltonian epsilon. And this can be simply achieved by, since this epsilon is a binary operator, this can be simply achieved by diagonalizing this fermion binary operator and then occupy some pseudo bands that are separated from the others. And we can easily see that such a state will be a unique eigenstate of the epsilon. And one can further show that such a state always have non-zero expectation value on O. So this complete the construction. I'd like to mention that not just in this case, not just the ground state, but also some few body excitations are largely solvable. Specifically, to solve excited states, we look for operators that satisfy commutation relation, this commutation relation when acted on the ground state, where E will be this energy of this excitation. And to solve such a C operator, we can use a peculiar property of this constructed model. That is, the commutation does not change the composition of the C operator you put in. For example, if you put in some single electron operator, the result is still a single electron operator. And if you put in a Cooper pair, it still generates a Cooper pair. So that's a peculiar feature of this specific model. It's not generic, but thankfully, we can use this property to solve the excitations for any composition sector. Because now, for each composition sector, it suffices to diagonalize a scattering matrix, gamma, that is only polynomially large in system size. So you can always obtain accurate numerical solution to this. Okay. Now, let's try to apply this general method to flat band problems. Specifically, we'll consider an energy hierarchy corresponding to isolated flat bands, meaning that the bands of interest have bandwidth W much smaller than the interaction strength V, which is further much smaller than the band gap delta separating the flat bands and the other bands, which we'll call remote bands. Then if you try the construction with your favorite autoparameter and favorite flat band, you will quickly find that it's in general very difficult to find a set of S operators that are local. So it's actually very difficult to construct interacting Hamiltonians in a meaningful way. So we need some extra condition on this electronic structure of the flat bands themselves for them to host meaningful solvable models corresponding to some autoparameters. Specifically, there's a set of sufficient conditions for the flat bands to admit the construction of solvable local interacting models, which I call quantum geometric nesting. Its definition is based on the quantum geometry of the flat bands. And here by quantum geometry, I'm talking a broad sense and referring to all the information stored in the projection matrix onto the flat bands on each K, which we'll call P of K. So what the definition really cares is the Hilbert space structure of the flat band and defined as this. So with all this preparation, we can now define the quantum geometric nesting as follows. We say that quantum geometric nesting at a wave vector Q in the particle hole channel to be satisfied if there exists a nesting matrix N such that for any K, the Hilbert space of the flat band and momentum K is mapped to that at K plus Q. And also the complementary Hilbert space for the remote bands also map correspondingly by this N. The point is that there's no cross terms when you act this N. And similarly, for quantum geometric nesting to be satisfied in the particle-particle channel, we need there to be a nesting matrix N such that for any K, the Hilbert spaces of the flat bands and the remote bands and momentum K are mapped to those at Q minus K with an additional complex conjugation. So you see that this concept is in direct analog to the concept of Fermi surface nesting in dispersive bands. Especially these rules of momentum transformation is the same. But here it is really about the compatibility of the Hilbert space. So which is a more meaningful concept to talk about in the flat band context because here we don't really have a well-defined Fermi surface. So yeah, we hope this will be a more useful concept there.
Is it right that this N is in general not unitary?
And does not need to be unitary. It could be, for example, it could be projective for the remote bands. because I don't really I don't have a lot of counterexample, but they don't need to be unitary in general.
You mean in many examples they are unitary?
Yeah, I will show you in a minute, but
Uh-huh.
yeah.
Just to make sure if n is unitary, then here we have two conditions for H and H bar respectively. If n is unitary, then only one condition is enough, right?
Yes, right. Yeah.
Mhm.
But in
Thanks.
general, it's not needed, although we
Mhm.
don't have many counterexamples.
Mhm.
Yeah.
Thanks. But sorry, just to make sure, you said you
Yeah.
don't have many counterexamples. Do you have any counterexample?
I mean, I can have some engineered counterexample. I can just have some trivial, remote band just manually put there. And then I
Ah,
just choose my n to be unitary within this meaningful Hilbert space and and ask it to be anything on the, manually added in Hilbert space, right?
that's
And in that case, n could be anything. It's a unitary tensor product with any matrix. Yeah.
okay.
Yeah.
Mhm. Thanks.
Because eventually we don't care about this remote band, right? So,
Mhm.
okay, let me give you a simple example. So let's consider two orbital 1D model with two flat band, artificial flat band given by this Hamiltonian. And it's defined by a zeta function of k, which simply specify where these eigenstates are on this big circle of the Bloch sphere on the xz plane, since we only use tau x and tau z here, the Pauli matrices. So then if you take this special choice of zeta of k, we find a very simple relation between the zeta at k and zeta at k prime, sorry, zeta k plus pi, that they simply differ by pi. And then this, in the quantum geometric nesting language, means that applying this tau y Pauli matrix on the eigenstate at k will map it to that at k plus pi. And since it will exactly do the needed pi rotation of the eigenstate on the Bloch sphere. And this means that the system have quantum geometric nesting for both bands, and in this particle hole channel at momentum pi. And the nesting matrix is just tau y. And indeed, it's hard for, this is an engineered example just to show you what we mean by Hilbert space nesting, right? And indeed, it's hard for quantum geometry nesting to hold exactly in a generic flat band, right? So we also figured out a way to quantify the distance to a perfect quantum geometric nesting for certain channel and wave vector, which we'll call nestability. And specifically, by using the P matrix of this flat band and its complement part, Q, we can define this 4-index tensor for each channel and each Q, which is very easy to compute for any flat band. And if you group the first two and the last two indices, the tensor can be viewed as a matrix which is positive semi-definite. We find that its smallest eigenvalue then provides a measure of the distance of the ideal to the ideal quantum geometric nesting for this flat band, because when the smallest eigenvalue becomes 0, this condition implies a perfect quantum geometric nesting. Yeah, so this quantity is a meaningful measure of the distance to the perfect quantum geometric nesting.
May I ask two questions? So can you remind me, why do you call it quantum geometric nesting? So usually when I think about quantum geometry, I think about all these superfluid stiffness and Chen number condition. Sorry, fraction chain sorted condition. But how should I see anything is related here?
So I've seen all these aspects you mentioned are properties of quantum geometry. The quantum geometry is defined by a notion of distance in momentum space, and specifically is defined by the trace of P at K and P at K prime, right? And you see that it's closely related to the definition here.
I
We're
see.
Yeah. Actually, in our paper, we have a lot of discussion on this nomenclature issue. Actually, each satisfied quantum geometric nesting define a generalized quantum geometry that's beyond the conventional definition. Yeah,
I see.
it means that it defines a measure for the distance in the momentum space.
I see. I see. In that sense, I see.
Yeah. But indeed, it's not the conventional quantum geometry. So that's why I said that I'm talking about quantum geometry in a general sense. Yeah.
I see. And second question is, in order to use the eigenvalue as a nestability measure, you must be using the fact that the projector operator is normalized or something, right? So there's no prefactor that affects it.
Oh, of course, I assume that P is projectors in the sense that P squared equal to P.
And then this is properly normalized. I see. Thanks.
Yeah. Yeah, there are a lot of actually technical subtlety in defining this quantity, but you can find all these fine prints in our paper. Yeah.
Thanks.
Yeah. Okay. Having defined this condition of quantum geometric nesting, let me now tell you the consequences of this. Firstly, if a flat band system has quantum geometric nesting, certain fermion bilinear order parameters will be suggested. Remember that this will be the center of this construction. Okay, and these order parameters are defined by the nesting matrix that you can solve from this procedure. And specifically, is nothing but the form factor expressed in this original orbital basis. And for each suggested order parameter, there will be two further consequences. The first is that if we compute the Baire susceptibility of this order, it saturates a theoretical upper bound, which indicates that they are the most likely ordering tendency among all the possible orders from a mean field perspective. However, remember that we are really interested in the flat band limit, which is strongly coupled. This mean field picture is actually at best suggestive. What is more important is that now there exist many valid choices of S operators that first commute with O and second are local. And then you can see that using this S operator, and you can apply the general construction, and they can generate an infinite family of solvable interacting Hamiltonians in this flat band limit. And again, I won't torture you with the general discussions of these S operators, but I do want to show you some worked out examples to illustrate how powerful this concept could be. Firstly, we know that this concept naturally unified, I would say, most of the known examples of solvable limits for flat band systems, which are mostly ensured by symmetry. The first kind of trivial example is that we observe that any flat bands with some conserved flavor indices have quantum geometric nesting at Q equals 0 in the particle hole channel, with the nesting matrix that's identity in the orbital basis and an arbitrary matrix on the conserved index. And this untilde matrix will specify the polarization of the conserved flavor. And the familiar example. Yeah.
I'd like to ask, what do you mean by conserved flavors here?
Yeah, for example, spin or valley or
Mhm.
layer. Yeah, any index that label the conserved charges. Yeah.
Okay.
Yeah.
Okay. Yeah.
Yeah, so a familiar example of this is the quantum Hall ferromagnetism. And a slightly more non-trivial observation is that flat band with some bipartiteness in the hopping structure have quantum geometric nesting in the particle hole channel at q equals 0 again, but now with this form of nesting matrices, where A and B label the two sublattices, and again, N tilde is an arbitrary matrix specifying the flavor polarization, and S primes are again the conserved quantity indices, and the conserved flavor indices. And the ideal interactions for both type of quantum geometric nesting include just local density operators. By a spinfold time reversal symmetry, or just a familiar Wannier degeneracy, which implies quantum geometric nesting in particle-particle channel at q equals 0 with a singlet pairing order parameter. And in this case, any density attraction will be an ideal interaction to stabilize this superconducting order, and as noted by these works. So you can see that this concept already nicely unify a lot of known examples, but I want to say that our construction allows us to construct even more interactions that are solvable for these systems, other than those that are already identified. A more interesting scenario is probably when quantum geometric nesting is coincidentally satisfied instead of just being ensured by symmetry. Actually, the toy example I just provided is such a case, although it's an engineered model, right? Now, let's see what the general construction can lead us to. It turns out that the general interaction in this case can be as simple as a density repulsion within each unit cell, which will give us an ordered ground state with this simple order parameter. And it turns out that this order parameter actually overlap with the current density operator, but not the density operator. So the ground state actually hosts persisting circulating current while being spatially uniform in density. So this is actually a current or flux density wave if you if you regard these two orbitals as the two legs of a ladder. And you can plot the current pattern like this. And in 2D, we also cooked up a toy electronic structure which is a bilayer construction on square lattice. And what is needed for the quantum geometry here is that the hopping elements on the two layers are of the same amplitude, but without these signs, and they are much weaker than a hybridization gap, hybridization M between these two layers. And in this limit, there are two spin degenerate flat bands with bandwidth T squared over M and a band gap M. And the quantum geometry in this model is very weak, but it suggests a perfect quantum geometric nesting in several different channels. So besides the q equals 0 particle-particle channel ensured by spinfold time reversal symmetry, there are also q equals to pi particle hole and particle-particle channel quantum geometric nesting, corresponding to charge or spin density wave and a pair density wave, respectively. And applying the systematic construction of the solo models, we were able to find a very simple interlayer interaction that only favor the pair density wave order, and it's simply interlayer attraction and some antiferromagnetic coupling. Then applying the standard solving procedure, we can solve the Cooper pair excitation actually exactly and analytically, whose lower branch clearly has a minimum at q equals pi. And you might be worried that now the bands are not exactly flat, so we performed a numerical calculation of the Cooper pair spectrum, taking into account of the leading order correction in bandwidth. And we find that the lowest branch is insensitive to these corrections, and the Cooper pair mass is roughly V times the quantum metric, which is much greater than just the bandwidth square over interaction. And this kind of clearly clarify that the phase stiffness in this model originates from quantum geometry instead of single particle kinetic energy. So it's not a just superconductor from conventional kinetic energy driven mechanism. Okay. So I would like to conclude by thanking all my collaborators. First of all, of course, my PhD advisor, Stephen Kivelson, who gave me a lot of guidance for both parts I presented today. And for the second part of the talk, many works are done in collaboration with Jonah at Princeton. And we also received many useful comments from his advisor, Andrew Bernimay. And now with Jonah and Islam at Harvard, we are further pursuing solvable models for flat band superconductors. And hopefully I will have many more things to tell you about soon. Okay, thank you for listening.
Okay, thank you, Zhaoyu, for the very interesting talk. Any other questions? Maybe let me start. I think you have already answered this question, but let me still ask, but maybe in a different way. Suppose I am interested in some particular symmetry breaking pattern, and I want to ask whether I can construct a good model for it. I think you mentioned there's no general strategy. Sometimes this strategy works, sometimes it may not work, but basically there are some particular symmetry breaking patterns that I'm particularly interested in, like on Kagome lattice or triangular lattice. There are some particular non-collinear magnetic orders and some valence bound solid orders that I'm particularly interested in.
Yeah.
And then if I want to find such a model to realize these orders, what should I do?
So it's probably not completely doable within this more restricted scheme, but hopefully with this the approach that will appear soon in this ongoing work, you can construct solvable model for any order parameter that you want. But the caveat is that the resulting interaction might look unnatural. Yeah, that's a price you need to pay.
Unnatural meaning what?
It's not close to anything that you're familiar with.
That's fine.
Not,
that's fine.
yeah. Yeah, if you don't mind that, then it's always possible. That's my response. And for detailed discussion, I will, work everything out very soon, hopefully.
Although it may be unnatural, but it can still be local.
Yes, it can be still local. Yeah.
Mm-hmm. Also, in your talk, you mentioned the two constructions, one for bosons, one for fermions. What about spins?
Oh, spins in my notion can be viewed as a bosonic system. As I briefly mentioned, this construction actually works for generic bosonic system, not just those, have charge conservation. You can
The dimension of the Hilbert space can be anything.
Yes.
I see.
So I actually have a suspicion that this conjugation method, starting from simple model, this conjugation method can actually unify all the known bosonic solvable models. But I don't have a proof, but that's my feeling. Yeah.
Thanks.
Hello, I have a question.
Yeah.
How can I understand the filling number? Because it seems like chemical potential will not affect the frustration, but we know for different filling number, we can get a different order. So how can we understand this?
Yeah, that's a great question. So I assume you are talking about the second approach. Is that right?
Yeah, right.
Yeah, so first of all, in the flat band, extremely flat band limit, chemical potential is kind of pinned there. It's as long as you're concerning the physics in flat band. And then the filling fraction for the solvable models are actually determined by the uniqueness of the ground state. You can see that here I require the electrons to occupy some isolated bands of this pseudo Hamiltonian, and that can only be satisfied for certain electron density, and that tells you the filling fractions are where this construction is relevant. So if you're familiar with twisted barrier graphing example, you actually, depending on like what limit you're taking, what ideal limit you're taking, you can have solvable model at either integer filling or even integer filling. So that really depends on all this, the details in the auto parameter you construct and all this quantum geometry. It's self-consistent. It's that like as long as I give as long as you give me the electronic structure, I can tell you everything.
Yeah, but I think your nesting condition does not define filling number, right? Because even though you don't know the filling number, you can also know what's the
Yes,
nesting
yes,
condition.
that's purely defined by the Hilbert space structure. What I was talking about is that the consequence is that you can only construct solvable model at certain filling fractions.
I see.
I
I
mean,
see. Thank you.
yeah, especially for particle hole channel. For particle channel, you can construct the same
Yeah.
Hamiltonian will have a solvable ground state at any filling fraction.
Yeah.
They're all degenerate.
Any other questions? Okay, if not, Zhaoyu, thank you again.
Thank you.
Thank you so much.
Yeah, I think we can now leave. Bye.
Thank you.